Hey everyone, ready to dive into some quantum mechanics. We're tackling particle motion today.
But not the kind you might be thinking of.
You're probably thinking like Newton's laws,
Hmm.
force, mass, acceleration.
That's the usual, right?
Exactly.
Hmm.
But in quantum mechanics, it's not quite that simple.
No, not at all. It's a whole different world. We're not talking about that neat x of t.
X of t.
Yeah. Finding a particle's exact position as a function of time, like in classical mechanics.
Oh, right. Like if you throw a ball, you know where it's going to land.
Exactly. Predictable. But in quantum mechanics, we look for the wave function instead.
Wave function.
It's represented by the Greek letter, and it doesn't tell us exactly where a particle is.
So it's not about a specific point then.
Nope. It's more about probabilities.
Probability. So we're talking chance, not certainty.
Exactly. The wave function gives us the probability of finding a particle at a certain point in space and time.
Okay, so it's like a fuzzy cloud of possibilities instead of a fixed point.
A great way to put it. It's a whole different way of thinking about how things move.
So how do we find this wave function? Is there like a quantum version of Newton's second law?
You got it. There's an equation for that. The Schrödinger equation.
Schrödinger. That rings a bell.
It describes how the wave function changes over time, like Newton's second law does for a particle's position.
Okay, so it's our key to understanding how the wave function behaves.
Precisely. And, of course, we can't forget about Planck's constant.
Ah, Planck's constant, another one of those quantum mechanics essentials.
It shows up in the Schrödinger equation, reminding us that we're dealing with the quantum realm, where things are very different.
All right, so we've got this wave function thanks to the Schrödinger equation. But how does it actually describe a particle? I always imagine particles as like tiny little points.
Right, like little billiard balls.
Yeah, exactly. How can something spread out like that tell us about a particle's state?
That's where the statistical interpretation comes in, a way to make sense of the wave function.
Statistical interpretation. Does that mean probability is back in the picture?
Absolutely. Developed by Max Born, it basically says the square of the wave function at a given point represents the probability of finding the particle there.
Okay, so if the wave function has a high value at a specific spot, it's more likely to find the particle there.
Precisely, like a landscape. Peaks and valleys. The higher the peak, the greater the probability.
Got it. So it's about likelihoods, not certainties. So even if we know everything about the wave function, we can't predict a particle's position with absolute certainty.
That's the fascinating thing about the quantum world. It's inherently uncertain. Unlike classical physics, where, in theory, you could predict everything perfectly.
Wild. Okay, so let's say we measure a particle at point C. The question is, where was it just before we measured it?
Now that's a question that has puzzled physicists for ages. It leads us to some very interesting interpretations of quantum mechanics.
Oh, interpretations. Sounds like things are about to get really intriguing. I'm ready to hear more.
Yeah, so there are a few main interpretations out there, and each one is trying to answer that question. Where was the particle before we measured it?
Okay, so let's hear them. What are the different explanations?
One interpretation is called the realist view.
Realist, okay.
Think Einstein. He was a big proponent of this idea.
Right, makes sense.
Realists believe that the particle was at point C all along. They say that quantum mechanics is just incomplete.
Incomplete, like it's missing something.
Exactly. They think there's some hidden variable, something we haven't figured out yet, that would tell us exactly where the particle is.
So they're saying it's not really uncertain, we just don't know enough yet.
Yeah, they believe that this indeterminacy, it's just a reflection of our limited knowledge, not a fundamental truth about reality.
Okay, I see. So what's the alternative to this hidden variable idea?
Well, the most widely accepted view is called the orthodox interpretation. Yeah, it's also known as the Copenhagen interpretation, and this one, it's a bit more radical. It says the particle, it wasn't anywhere definite before we measured it.
Wait, not anywhere. How's that even possible?
I know, it's a tough one to wrap your head around.
It really is.
But according to the Copenhagen interpretation, it's the act of measurement itself that forces the particle to choose a position. Before we measured it, it existed in a superposition of states, like a blend of all possible locations.
So it's like the particle was in this blurry state of potential, and our measurement, it forced it to collapse into one definite reality.
Yeah, that's a great way to put it. It's like the particle doesn't have a specific location until we, the observers, force it to pick one by measuring it.
Wow. So we're talking about observation actually shaping reality at the quantum level. That's a pretty profound concept.
It is. It's one of the most fascinating and counterintuitive things about quantum mechanics.
Yeah, for sure. So for a long time, these different interpretations were just like philosophical debates.
Right.
There wasn't a way to test which one was actually correct.
Yeah, that's true. But then a physicist named John Bell came along.
Congo, okay.
And in the 1960s, he developed Bell's theorem.
Bell's theorem.
And it showed that these different interpretations, well, they actually have distinct observable consequences, so we could finally test them.
So he turned a philosophical argument into a scientific experiment.
Exactly.
That's brilliant. So what did these experiments tell us? What was the verdict?
The experiments, and they've been repeated many times, very precisely, they have overwhelmingly favored the orthodox view.
The Copenhagen interpretation.
Yep, that's the one.
Okay, so it seems like measurement really does influence a particle's reality.
Yeah.
It's not just passive, it's like we're participating in shaping the quantum world.
It really does seem that way.
Okay, so let's say we measure a particle and we find it at point C. If we measure it again, like right after, will we get the same result?
That's a great question. And what's interesting is that repeated measurements on the same particle, one after the other, they will always yield the same result.
So once we peek at it, it's locked into that position. Like the particle's decided, okay, I'm here now.
That's a good way to think about it.
So how do we explain that?
We explain it through the concept of wave function collapse. So when we make a measurement, the wave function, remember, it was spread out, representing all those possibilities, but suddenly it collapses into a sharp peak right at the point where we found the particle.
So it's like the wave function suddenly knows where the particle is.
Exactly. And it concentrates all of its probability at that point.
But what happens if we wait a while and measure it again? Will it still be there?
Well, that's where things get interesting again, because over time, the wave function, it'll spread out again, according to the Schrödinger equation. It's like the particle's position becomes uncertain again.
Okay.
But if we make a second measurement and we do it quickly enough before it has a chance to spread out too much, we will find it in the same spot.
So we have these two processes happening.
Right.
The smooth, continuous evolution of the wave function, governed by Schrödinger's equation, and then these sudden, discontinuous collapses when a measurement takes place.
Exactly. That's the strange duality of quantum mechanics. The universe is playing a game with two sets of rules, and it switches between them depending on whether we're looking or not.
It's mind-boggling, but fascinating at the same time.
Definitely.
So are there still unanswered questions about all of this?
Yeah.
Are there still mysteries in the quantum realm?
Oh, absolutely. There's so much we still don't understand.
Like what are some of the big puzzles that are still out there?
Well, for one, we still don't have a clear definition of what a measurement actually is. Does it require a conscious observer? Or could it be any interaction with the environment? These are big questions, both philosophical and scientific.
Yeah. It seems like the deeper we go into quantum mechanics, the more we realize how much we don't know. It's pretty humbling.
I know, right? It really makes you question everything.
It makes you realize how much we still have to learn.
Absolutely.
So we started out thinking about like baseballs and how things move.
The familiar world.
Right. And now we're in this crazy quantum world with wave function collapses and the mystery of measurement. It's a big leap.
It is. We've gone from classical mechanics, where everything's predictable,
Yeah, neat and tight.
to this quantum realm where probability rules and where measurement itself plays a role in shaping reality.
Yeah, it's a whole new way of thinking about how the universe works.
Definitely a paradigm shift.
So to wrap things up, what are the big takeaways from all of this?
Well, I'd say the most important lesson is that in the quantum world, we have to let go of certainty.
Embrace the uncertainty.
Exactly. We have to accept that reality, at its most fundamental level, is probabilistic.
And that when we observe something, we're not just passively watching, we're actually participating in shaping that reality.
That's right. The observer and the observed are not separate. We're all part of this quantum dance.
Well, this has been an incredible journey. It's amazing to think that just by looking at something, we could be influencing it.
It's mind-blowing, isn't it?
It really is. And who knows what other amazing things we'll discover as we explore this quantum world further.
There's so much more to learn.